Hello, everybody, and welcome to episode 3.3. This episode is a continuation from episodes 3.1 and 3.2, and today I am introducing the concept of marginal economics. You can catch up on episodes 3.1 and 3.2 by clicking on the link in the video, and please don't forget to hit the subscribe button below. Marginal economics is the concept that deals with how a business views or values the trade-offs associated with incremental activities. Incremental activity is often described by a tiered or layered system of inputs and outputs that have differing levels of pricing or volume. Take the simple depiction to the right as an example. As we have seen in previous episodes, we have a set of inputs or raw materials that is sent to a collection of processes used to manufacture products for customers. Here we can see that for some of our inputs, we might have multiple suppliers offering that input at different levels of pricing and availability. The same can be true for outputs, where we could have multiple markets or customers for a given product offering different demand levels and prices. Today's episode will build on the problems from the earlier episodes in this series and demonstrate how to consider this situation in an optimization problem. We'll start today's problem by revisiting our problem description and noting the changes that we made for today's episode. For those that were with us in episodes 3.1 and 3.2, you'll recall that we're dealing with a firm, RMC Incorporated, that produces a variety of chemical products. In their production process, 3 materials are mixed together and heated at 300 degrees Fahrenheit to produce 2 products, a fuel additive and a solvent base. Each ton of fuel additive is a mixture of 0.4 tons of material 1 and 0.6 tons of material 3, and a ton of solvent base is a mixture of 0.5 tons of material 1, 0.2 tons of material 2, and 0.3 tons of material 3. There are multiple markets for these products, however, the demand and pricing varies. After deducting relevant costs, the profit contribution in premium markets is $44 for every ton of fuel additive produced and $38 for every ton of solvent base produced. For discount markets, the profit contribution drops to $15 for every ton of fuel additive produced and $20 for every ton of solvent base produced. RMC has 2 mixing units available for production of fuel additive and solvent base. These mixers operate 6 hours a shift, 3 shifts a day, 7 days a week. Both units can mix solvent base or fuel additive. The newer Mixer 1 rate is faster than the older Mixer 2 unit. While materials 1 and 2 are procured solely from vendors, material 3 is an intermediate product which can be manufactured on-site or procured from vendors. On-site manufacturing requires utilizing 2 flashing units to produce material 3, which is a stabilized version of material 4. The flashing unit operates by heating material 4 and then flashing it under pressure to remove volatile compounds and stabilize the material. The volatile compounds are a byproduct, and RMC pays a small fee for a local power generation facility to incinerate this gas in accordance with the local environmental regulations. The flashing unit operates 6 hours a shift, 3 shifts a day, 7 days a week. The vendors supplying material 3 have a limited availability and offer significantly different pricing. The planning department is working to determine the production plan for the coming week, provided the current pricing, current availability of raw materials, and existing equipment capacities. The depiction of the problem statement above is shown here. As you can see, we have our raw material 4, which is fed to flashing units 1 and 2 to produce material 3 and our byproduct gas. Materials 1, 2, and 3 are then mixed in either units RX1 or RX2 to produce our products, a solvent base, or a fuel additive. We can now move on to further define the problem. Under the problem definition, we've made a list of information required to solve this problem. Some of this is a restatement from the problem description. We'll review each of these. Premium market sales yield $38 per ton of solvent base and $44 per ton of fuel additive. The demand for these products is 75 tons and 50 tons respectively. Discount market sales yield $20 per ton of solvent base and $15 per ton of fuel additive. The demand for these products is 25 tons and 15 tons respectively. This is where we start to actually see the first introduction of the concept around marginal economics. We have two different markets offering two different prices for these products and at varying demand levels. We know that 1 ton of solvent base requires 0.5 tons of material 1, 0.2 tons of material 2, and 0.3 tons of material 3. We know that 1 ton of fuel additive requires 0.4 tons of material 1 and 0.6 tons of material 3. We are maximizing profits for a single period, and we are still not considering any multi-period sales. Our on-hand material availability is 150 tons of material 1, 100 tons of material 2, and 0 tons for material 3, and 150 tons of material 4. Material 3 can be produced at 0.2 tons per hour, and the yield loss for stabilizing material 4 is about 0.1% by weight. The mixer 1 production rates for solvent base and fuel additive are 0.8 tons per hour and 0.65 tons per hour respectively. And for mixer 2, the production rates for solvent base and fuel additive are 0.75 tons an hour and 0.6 tons an hour respectively. The total production time available for mixer 1, mixer 2, flashing unit 1, and flashing unit 2 is 126 hours each. Additional material 3 is available for purchase from two different suppliers, A and B, at a price of $20 per ton up to 8 tons and $37 per ton up to 15 tons, respectively. Again, here's another piece of information where we're introducing some marginal economic considerations. We have a single material being supplied from two different vendors at varying prices and varying availability. Additional operating time for each process is not available since scheduling is at capacity. And for our opportunity statement, nothing has really changed. We're continuing to maximize the profit by determining how much of each product, solvent base, and fuel additive we can produce within the existing equipment capacity and with the raw materials available. So with our problem defined, we're ready to move on to model development. So here we're going to start on the left and go through the different variables and sets for our problem. We're going to let F equal our product fuel additive and S equal our product solvent base. We're going to let M1, 2, 3, and 4 represent our material inputs for materials 1, 2, 3, and 4. We're going to let B1 represent our byproduct 1 produced from the processing of material 4 to make material 3. We're going to let RX1, RX2, FD1, and FD2 represent our pieces of equipment for product mixer 1, product mixer 2, flashing unit 1, and flashing unit 2. We're going to let I represent a set of products that we make or manufacture in our processes, which includes the solvent base, the fuel additive, and material 3. And we're going to let J represent the set of material inputs to our processes, which includes materials 1, 2, 3, and 4. We're going to let S represent our suppliers of material 3, supplier A and B. And we're going to let Z represent a set of byproducts produced in our processes, which at this moment only includes byproduct B1. And we're going to let K represent the set of equipment involved or the set of processes for our facility, which includes both mixers and both flashing units. P sub I is going to be a variable representing the profit of product I. C sub Z is going to be a variable representing the cost of producing byproduct Z. We're going to let Y sub IK be a decision variable that represents the amount of product I manufactured by process K. We're going to let D sub I as a variable represent the maximum demand for product I. We're going to let W sub Z represent the amount of byproduct Z produced. We're going to let Q sub JS represent a decision variable that will be the purchased material J from supplier S. X sub IJ is going to be a variable or a coefficient representing the material J consumed per ton of product I produced. B sub ZI is going to be a coefficient representing the byproduct Z produced per ton of product I manufactured. R sub JS is going to be a variable representing the rate of material J or the price or cost of material J from supplier S. And we're going to let A sub JS represent the material J available from supplier S. M sub J is going to represent material J available. That's going to be our opening or on-hand material. T sub K is going to represent the time available for equipment A. And R sub I K is going to represent the production rate for product I on equipment K. Got a couple typos here I'm going to fix really quick, so I'm just going to pause for a second. Right, so with our variables and parameters now defined, we're ready to move on and develop our mathematical model. The first component is the objective function. Again, this is our objective here is to maximize profit. And our profit is going to be defined by three various terms. So this first term we've seen before. This is the profit for selling or manufacturing product I times the amount of product I made on equipment or process K, so Y sub I K, and we sum that up across all products and all pieces of equipment. So this gives us a total products made in the entire facility multiplied by their profit contribution. The next term is the cost of any byproducts made from manufacturing our products multiplied by the amount of byproduct made. So C sub Z times W sub Z for all byproducts in set Z. So this would be a negative contribution to the profit. And then we also now have this third term, which is also going to be a negative contribution to our profit because it's going to represent the price of material J from supplier S, R sub JS, times the amount of material J procured or purchased from supplier S. And we take R sub JS times Q sub JS, and we sum up all of the material purchased from that supplier at that rate for all suppliers in set S and all materials in set J. So these three terms are basically our profit generated from making and selling products, minus the costs of processing our byproducts and purchasing additional material from vendors. We have three decision variables in our model: Y sub I K, which is going to represent the tons of product I produced by process K; W sub Z, which is going to represent the tons of byproduct Z produced per ton of I; and Q sub JS, which is going to represent the tons of purchased material J from supplier S. For our constraints, we have some additional constraints than we did in the previous episodes. The first one we're going to cover we've had, which is our material balance constraint, and it's slightly different than the previous episodes. So on the left-hand side here, we still have X sub ij, which is the amount of material J consumed in the production of product I, multiplied by the amount of product I made on machine K, which is Y sub ik, and that is summed up for all products I in set I and across all processes in set K. And that gives us the total amount of material J consumed. And that has to be less than or equal to the material that's available. And that is made up of three different contributions. So the material available is the summation of our M sub J, which is the opening inventory or on-hand inventory of material J, plus any material J that we produce upstream. So Y sub JK is the amount of material J produced on machine K for all machine K, for all machines in set K. So if we recall our depiction up here, there's only one serial process, which is the production of material 3 from flashing units 1 and 2. So for material 3, this Y sub JK would represent the amount of material 3 produced on flashing units 1 and 2. And then we also have here the additional material that we might purchase or procure from our suppliers. And so that's going to be the summation of Q sub JS, which is all the material J procured from all the suppliers that supply material J in set S. And then we're going to do that for all materials 1, 2, and 3. And 4, sorry. For byproducts, this is actually it's a constraint that defines one of our decision variables, W sub Z, so it's also a material balance, but it's slightly different. So for all product I made on machine K, so Y sub ik, summed up across all products I and all processes K, multiplied by the coefficient B sub Zi, which represents the amount of Z made per product I, gives us W sub Z, which is going to be the byproduct sub Z, and that is going to be done for each different byproduct. Again, recalling that we only have one byproduct right now, B1, which is the gas produced from processing material 4 to make material 3. And so this would end up being W sub B1 multiplied equal to B sub B1, and that's associated with material 3, making material 3 multiplied by Y sub IK. Again, I here would be material 3, and K would represent flashing units 1 and 2. For production time, we actually want to sum up all of the different amounts of materials, product I made on each machine K, divided by the rate of making, or how fast we can make material I on machine K. So the tons of I made on K divided by the rate of I on K gives us time in hours. And that has to be less than or equal to the actual available time of machine K that we've set in the problem definition. And we do that for, and we sum this up, this left-hand term up, we sum that up for every product that we make. So everything in set I. So if machine K is making multiple products, whether it's solvent-based and fuel additive, you would sum it up for both of those. And we would do that for each different machine in set K. As a side note, I do also just want to acknowledge that I am using the terms process, equipment, and machine interchangeably. In the context of this problem, there is no distinction between them. They're all interchangeable. In future problems, there may be a difference, in which case I'll make that distinction clear. But if you hear me say process, machine, or equipment, just be aware that they all mean the same thing. So the next constraint to talk about is this product lower bound. So this is simply a non-negative constraint. So we know that we cannot produce any negative amounts of product I on any of our machines. So Y sub IK has to be greater than or equal to 0 for all combinations of I sub K. So again, we do that for each IK. We also now introduce a new constraint on our products. So in the past episodes, we've only had this non-negative production constraint, but we actually now have a product upper bound. And again, this has to do with the concept of marginal economics, where we defined earlier D sub I, which is the maximum demand for product I. So what we end up doing is saying, hey, for Y sub IK, summing that up across all machines, so the total amount of production of product I, that has to be less than or equal to the total demand D sub I for that given product. And we do that for each product. We also have a byproduct lower bound. W sub Z has to be greater than or equal to 0. And we do that for each byproduct. Again, this is very similar to the product lower bound, just a non-negative constraint. And then we also now have a new constraint for material upper bound. So Q sub JS, which is again the amount of material J we procure from supplier S, has to be less than or equal to the availability of that material J from that supplier. So as I noted earlier in the problem definition, we have a certain availability of material 3 from each of the different suppliers. And so whatever we procure has to be less than or equal to what's available from that supplier. And we do that for all JS. And so that is our mathematical model. So again, if you're with us for previous episodes, you'll see some new constraints here: the product upper bound, the material upper bound that are associated with the marginal economics, and of course, the change to our material balance with the procurement of K sub JS, which is again the amount of material J procured from supplier S for all suppliers that supply material J, and the change to our objective function by including now this term, the negative contribution to our profit, which reflects the cost of all materials we are procuring from these different suppliers. So with that, we're ready to move on to the Python section. As I've noted before, first thing we always do is import all the necessary libraries we need: pandas for managing our data frames, numpy for any numerical calculations or processes we might need to do, and then pulp for building our linear program or mathematical model object. So after we do that, the next step is to read the data, and I'm going to pause here and pivot over to Excel so we can just take a walk through the data set so you can see what's changed with the introduction of this marginal economics concept. So our data set has a lot of the same tables as before, but a lot of them will be different because of the marginal economics, again, we're trying to discuss in this episode. So the first table, which is products, again, represents all the different products that we make, the price of that product. And now we've introduced 3 new columns, a min, a max, and a tier. So the column A represents the product we're going to produce. Column B represents the price for that product that's associated with column E. So what tier of sales or market are we talking about? So in this context, the tier 1 products, S and F, represent our premium markets, and the tier 2 products for S and F represent our discount market. So for the premium market, we can sell solvent base and fuel additive at $38 and $44 per ton respectively, up to a maximum demand of 75 and 50 tons respectively. For the discount market, we can sell solvent base and fuel additive at $20 and $15 per ton respectively, up to a maximum demand of 25 and 15 tons respectively. And again, that represents our discount market. And of course, material 3, which is an intermediate component, we're not pricing that. And we don't have any outlets or any markets that actually procure that intermediate, or that we could sell that intermediate product to. So these are left blank. For the materials, not a lot's changed. So just again, a list of our materials in column A and the on-hand availability. This is M sub J that we have to start our problem. Purchase is a new table. So this table actually represents the variable, or I should say the optionality that we're introducing around suppliers and being able to procure some materials. So for simple reasons, we're just gonna make sure that M1, M2, and M4, we're gonna say that we have a supplier A, but there's actually no availability. So the maximum amount of materials we can purchase for M1, 2, and 4 are 0. But supplier A and supplier B do have some material 3 on hand they're willing to sell us at a price of $20 per ton from supplier A up to availability of 8 tons. Supplier B is willing to sell us material 3 at $47 per ton up to a maximum of 50 tons. We have our recipe table here. Again, nothing has changed from previous episodes. We have our products that we're making in column A, the material input or list of material inputs into that product, and then of course the coefficient of consumption. So as noted earlier, when we make solvent base, we consume 0.2 tons of material 2. Our byproducts table, similar to our products table, represents the byproducts that we make and of course the costs associated with that byproduct. Our unit rate table lists all of our processes, machines, or equipment, the products that you can make on those various processes, machines, or equipment, and then the rates in tons per hour that you can make them at. So again, if we wanted to make fuel additive on mixer 1 versus mixer 2, the difference is 0.6 tons versus 0.65 tons per hour rate. And for flashing units 1 and 2, they both have the same rate for making material 3, 0.2 tons per hour. And then finally, we have our unit capacity table. This again just represents the unit or the machine or the process or equipment that we have available and the amount of time that we have to operate that machine. So this 126 hours represents that 6 hours per shift of operational time on an 8-hour shift, 3 times a day, 7 days a week. So now we're gonna pivot back to the Python, the Jupyter Lab notebook, and walk through the Python code. As with our previous episodes, I'm going to start by walking through our code. I'm going to move a little quicker though than I have previously, since a lot of this code has been covered in past episodes, but where appropriate for the context of this problem in terms of marginal economics, I will point out anything that's important. So first and foremost, we bring in our libraries, again, pandas for managing our data frames, NumPy for any numerical methods we need, and pulp for building and constructing our mathematical model. I'm going to read in the data from our Excel file that we just covered. So that will include our products, byproducts, materials, recipe, unit rate, unit capacity, and purchase tables. And for the first table, the products table, I'm going to do a data transformation right out of the gate. So the first thing I'm going to do is create unique variable names for each of the product and sales tier pairs. So as I just covered, we have two different markets for our solvent base and fuel additive. We have a premium market, which we're calling our sales tier number 1, and our discount market, which we're calling our sales tier number 2. And so I'm going to loop through each of these rows, and where I have a product and a tiered market, I'm going to create a unique variable name. And it's pretty straightforward. It's going to be S_1, F_1, S_2, F_3, or sorry, F_2. And of course, for our intermediate component, since we're not selling that and we don't have any tiered markets, we just retain the original product name. And that's how we're going to actually construct the variables P sub I and Y sub I K later using these variable names. No transformations necessary for the materials table. For the recipe table, just like last episode, I do one transformation where I split the table up between a yield table and a recipe table. The yield table represents any of the product material pairs that have a negative consumption coefficient. This represents the generation of a byproduct. So again, here, when we produce our M3 material, we generate a byproduct B sub B1. And of course, that coefficient is a negative 0.001 tons of B1 produced per ton of M3. The rest of the recipe table is your positive coefficients, and again, represents the amount of material consumed when in producing either one of our products, solvent base, fuel additive, or material 3. And what you'll notice here is that to generate this table, I did a left merge with the recipe table, or sorry, with the products table. So on the left, I use the recipe table, and then I merge the products table, and I merge them on the product key. And what that then gives me is a new recipe table for each of the unique variable names that I specified earlier. So S_2 will have all of its recipe along with S_1, and of course those recipes are identical. But doing it in this way makes it much easier to deal with building a mathematical model later. In terms of the unit rate table, I actually do the same thing. So I have my unit, the product that I'm making on that unit or can make on that unit, and the rate at which I can make it. And I also, again, here do a left join, merge the tables on product, and that again gives me the replication of that unit product rate table across the unique product names that I created earlier. No changes to the DF unit capacity, and no changes to the DF purchase table. So again, this table just represents the amounts of the materials that I can procure, in addition to what I have on hand from which supplier, at what price, and of course at what volumes that's available. And so now I'm ready to construct all the dictionaries in order to build my mathematical model. And we've covered the construction of these dictionaries in the past. So I'm going to skip down here to the end and talk about the two new dictionaries, which are R and A. So again, R sub JS represents the cost of material J from supplier S. And again, I use the DICT in conjunction with the zip function in order to create a dictionary that for each individual material, which will be our primary key, we'll have a set of subkeys, which will be suppliers, and then the values within this table will represent the cost of that material from that supplier. And then I do something very similar with A. I create the same dictionary, which again will have the primary keys will be the material, and then the secondary keys will be the supplier, and the values will be the amount of materials that I can get, the amount of material I can get from that supplier for that material. And so, as always, I inspect the construction of these dictionaries to make sure that they are produced correctly. And we can see up here for X sub ij, everything looks good. I have my unique products, S_1, F_1, S_2, F_2, and then the recipe or the coefficient consumptions for each material. M looks correct, P looks correct. Again, seeing the correct unique variable names here. D, I forgot to cover that up here, but D is the demand. Sorry, that is a new parameter. So D sub I is going to represent the available demand from customers for each of our products. So S_1, we have 75 tons, F_1, 50 tons, and then so on and so forth. We have R sub ij, which again represents the production rate of different products on each respective machine. TB are look correct. Again, we've seen those before. Same with our C dictionary. And now we get to the other new dictionaries, R and A, and we can see again, as I mentioned earlier, we've correctly listed the materials, and 1, 2, 3, and 4 is the primary keys. The sub keys or the secondary keys are going to be your suppliers, and then the price. So we can see for M3, we have our two suppliers, A and B, and then the cost of those different of that material 3 from those suppliers at $20 and $47 per metric ton. Similarly for A, we see the availability of M3 from suppliers A and B at 8 and 50 tons respectively. So now we're ready to move on to build and solve our model. So step 1, as we've covered before, we're going to actually create an object, a model object. We're just going to call that object model. We're going to title the problem production resourcing and specify the type of problem, which is maximizing a problem. We want to maximize our profit. Then I'm going to move on to create the decision variables. So the two indices I'm going to use to make my a couple of my decision variable classes. I have my product index. Again, this is a nested list that includes the pairing of each product and unit. Again, the products that I can make on each of the different machines, pieces of equipment, or processes. And again, I use machine, process, and equipment interchangeably in the context of the series or problem. And I just want to make sure folks understand that that may not always be the case in the future, but here there's no distinction. So when you hear me say process, machine, or equipment, just assume they are the same. So I create the product index, and that's actually used to create the Y sub ij, right? Because again, I'm going to make a set of decision variables for each product I that I can make on each machine J. And so that's the index I use to loop through and create that set of decision variables, all with a lower bound 0, all continuous. For the raw index, this is going to be used to create our new decision variable Q. Again, this is also a nested list. So I'm going to have our material and supplier pairs in this index. And so I use that raw material index to make Q sub JS, again, for each material and supplier pair, all with a lower bound 0 and all continuous. And then before, as we've talked, I also have my Y sub Z decision variables, which represent the byproducts I make from producing different products. And in this case, it's only one. So I just do this. I create a decision variable W for every byproduct in the list, lower bound 0, continuous type variable. Now for Q, as we covered in the problem statement, I do have a maximum amount of material that I can actually procure from each vendor. So what I'm going to do for each of my Q sub JS decision variables is I'm going to also now add an upper bound, which is going to be different for each, by looking back at that dictionary, that A sub JS, and assigning that value, the maximum available material value, to this decision variable. So it will now have both a lower bound and an upper bound. And then I'm going to go ahead and inspect each of these decision variables, so make sure they all were built correctly. So I can see here my Y decision variable is correct. I've got decision variable for each of my unique product names, including material 3. So those all look correct. W is correct. I have a single decision variable, W sub B1, since I'm only making one byproduct. For the new decision variable, Q sub JS, this looks correct. I can see for materials 1, 2, and 4, I only have a single supplier A. But for material 3, I have 2 suppliers, supplier A and supplier B. So that looks correct. And now we're ready to move on and build our objective function. So we covered this earlier with the mathematical model, but there's 3 terms. So this first term represents the profit from producing and selling our different products. So we have our Y sub PK. P in this case would represent the I in the model, but this is the amount of material P made on machine K, multiplied by the profit contribution of that product P. And then we're going to sum that product between Y sub PK and P sub P up for all P and K in our product index. We're going to do the same thing down here for the next term, which is going to represent a cost or a negative contribution to our objective. So we're going to sum up the amount of byproduct W sub B multiplied by the cost of that byproduct, C sub B, for all byproducts in our model. And then finally, the new term here for the procured materials, again, a negative contribution to our overall profit. We're going to sum up Q sub MS, which is the amount of material M procured from supplier S, times the cost of that material from that supplier S. And I want to note the negative convention here. So in the data set, I had just put the positive values for the cost. So in order to represent this as a negative contribution, I have to make sure that I'm keeping with the correct convention and put a negative sign. Now, if I were to just say represent the cost as a negative value in the data set, this would not be appropriate. So it's a personal preference, really, but whatever you do have to be consistent with the signage. So then we're going to sum up the amount of material M from supplier S times the cost of that material M from that supplier S for all of our materials and suppliers in the raw index, and then add that objective function to the model. And for the constraints, again, we're going to walk through each of these. Some of these are familiar. So this first one is the material balance constraint. On our left-hand side up here, we're going to have the amount of material M consumed for all the production of product P on machine K. So we take X sub PM, the amount of material M consumed per ton of product P, times the amount of product P made on machine K. And we're going to sum that up for all PK in product index. And so this will represent the total amount of material M consumed. And that has to be less than or equal to M sub M. This is our M sub J in the model, which is the amount of material M that we have on hand or our opening inventory, plus the amount of material M made in any upstream processes. So for our problem, this is only true for material 3. We have the flash drums 1 and 2 that process material 4. So we're going to take Y sub MK, the amount of material M made on machine K, for all K in R sub M keys. And so all this really does is it tells us what machines we have available to make material M, and that's what we loop through. And we add all of that up, and that gives us a total material M that we can produce in our overall facility. And then, of course, if we don't have that material available in any upstream processes, then we just assign a value of 0, which essentially says, hey, we can't make this, so we're just going to consider the on-hand inventory. Plus now this third term, which represents any material we purchase from a vendor. So again, if we can procure a material M from a supplier S, then we need to take that into consideration in our material balance. So we take the sum of our Q sub MS, so all the materials all material M we can buy from supplier S for all suppliers and R, capital R sub M keys. So again, all the suppliers that actually supply material M will sum all the purchases up across those vendors, and that will give us the third term of our material balance in terms of availability. So in summary, the amount that we consume here has to be less than or equal to the on-hand inventory plus anything we're making ourselves plus anything that we buy from the vendors. And then, of course, I name this material balance for this specific material, and I repeat that for all M in materials. So for each material, I have a separate constraint. For K in units, this is our production time constraint. We've covered this before a couple times, and not a lot's changed. We're essentially saying for all of the material P we make on machine K divided by the rate that we can make that material on K gives us hours of production time on that machine K. We're summing that up for all the different products we can make on that machine, gives us the total amount of time that we're asking for or operating that machine for, and that has to be less than or equal to the total amount of time T sub K that we have available for that machine, and that's our production time constraint. Again, here we've got for B and byproducts. Here we're essentially saying that we have to look at all of the products we're making, Y sub PK, across all of the different machines, and then for each of those products, right, that have a byproduct associated with it, B sub BP, we're going to multiply this coefficient, that's the byproduct generation coefficient, by that value, and that gives us the total amount of byproduct made, W sub B, and then we name that byproduct underscore B. And then we have a newer constraint. So as we covered before, all of our decision variables have a lower bound constraint. They can't be negative, so they're all constrained to being at least 0 or greater. But as we introduced with this concept, or as we introduced in this problem related to marginal economics, we now have actually a maximum demand for our products as well. So there's not this infinite demand out there. So we also have to now impose a maximum product demand constraint. And the way that we do that is we take the total product P made on machine K, and we sum that up for all the different machines making that product, right? And so that gives us the aggregate product Y sub I, or aggregate product P, so that all the solvent base or all the fuel additive, and it takes us, we take all of that together, and that has to be less than or equal to the total demand. So for example, you would have on this side the total sum of solvent base, or S_1, that's sales tier 1 for solvent base, has to be less than or equal to the total demand for sales tier 1 solvent base. And that we're labeling max product for product P. So now we've made all of our constraints. We're ready to now write the model out. So again, I always recommend doing this, especially if it's a model that's readable, meaning it's not overly complex in size. I mean, some problems you'll start getting tens of thousands or thousands of different variables, and in that case, reading through a text file is going to be somewhat prohibitive. And there's other ways to validate that you've made the model correctly, but for these simpler models, it's a good habit to generate this LP and then read through it and make sure it looks correct. So the first thing I'll note is the objective function up here. Looking through this, it looks correct. I'm seeing my unique variables, y sub f1, y sub f2, y sub s1, y sub s2 on each different machine, and they have the correct profit contribution coefficients, or the prices correctly assigned. So now we are properly considering the different sales tiers. I also see I still have my costs associated with my byproduct, and I also now have the costs associated with material 3 being procured from either vendor A or B, and that cost coefficient correctly assigned. So this looks like it's been built correctly. I won't go through all of these. I've already done it. They are all built correctly, but I will note down here we also see now the additional bound that we've placed, the maximum bounds we've placed on our supplier material availability. So we can see here Q sub M3A and Q sub M3B, we see less than or equal to 8, again, correctly representing the maximum availability. So everything here looks in order. With that, we can move on now to solve the model. So to do that, we do model.solve, we assign our solver. I've covered what these settings are in the past, but the message true essentially is lets me know if there's a weird error or something that stops the problem early. I can see that in my Anaconda prompt. Key files equals false, just keeps my directory from being spammed with a bunch of other files. And then once I solve it, I want to check that I got an optimal status, and I did, so that's good. And I see that I have an objective value now with model.objective.value of 5,314 and about 80 cents. So that is the final optimal solution for this problem. And as I've done in the past, I'm going to walk through the variable results by constructing a data frame and storing all the different values, and then also do that for the constraints. So for the variables, I'm going to point out a few things here as they relate to the marginal economics. So the first thing I want to point out is we can see for our new variable, Q sub JS, we actually see that we are procuring or purchasing all the material 3 from supplier A that they have available. That's that 8 tons. And we see that there's a reduced cost associated with that at $27 per ton. Now, if you recall, or if you watched my first video where I introduced some basic principles of mathematical optimization, I had talked about what reduced cost was, and that essentially reduced cost applies only when a decision variable is 0, and it can, or at least is not bound, there's no upper bound. If that decision variable is 0 with no upper bound, then you'll get a reduced cost, and that represents the change in profit contribution or objective function coefficient required for the model to choose making more of that decision variable, or choose a value that's not 0. So if you had 0 M3A here and reduced cost of -5, it would say, hey, that price needs to come down by $5 in order for the material to choose it. But here we're on the different end of the spectrum. We're actually seeing that the upper bound, which is also new in this problem, the upper bound on this decision variable is binding or constraining the problem. And so now we also get a reduced cost in that situation. And that reduced cost is better thought of as a shadow price, shadow value. And what that means is, hey, because this is constraining, similar to what we think of it with dual values, what is an additional ton worth for this upper bound? So if I were to relax this upper bound from 8 to 9, I'd get another $27 in my objective function. And we can do that very quickly by changing the value from 8 to 9. So I'm going to go do that just to demonstrate this and be right back. Okay, so I've pulled up the purchase table from our data set. I'm going to change this 8 to a 9. I'm going to save this. I'm going to come back to this and I'm going to rerun the whole thing. And we're going to see if our objective function, which was 5314, goes up by $27. And it does. So instead of 5314, we have 5341. And we can see that indeed that shadow price of $27 was accurate. And so that's essentially how you would read a reduced cost for a decision variable where the upper bound is binding. I'm going to go ahead and change this back just for the sake of not changing our problem here at the end. Rerun it, and we'll see again the same results as we had before. So that's the first thing to note. The other thing I wanted to note is that while we purchased all of the supplier A material 3, we didn't purchase all of the supplier B material 3. And there could be a couple reasons. There could be economic reasons. There could be other constraints. So the first thing I want to check is, do we have any production constraints? Did we max out all of our machines? Is that why we're not purchasing any additional material 3 from supplier B? If we come down the constraints, we can see pretty readily that we don't have constraints here. So, we're maxing out FD1 and FD2. Those are totally maxed out, which is why we were procuring material 3 from those vendors, right? So that makes sense. But we're not maxed out on our mixer 1 unit, RX1. We have spare capacity there. So that suggests that the lack of procurement from supplier B or not filling out the total demand is more economic related. So we can come back up here and try and understand that. So to understand that, we come down to our product decision variables, and we'll start with S because it's pretty straightforward, but we can see that for our sales tier for S in terms of the premium market, so sales tier 1, we are maxing out all of that. We're making all 75 tons available in that premium market for solvent base. We're making it and selling it. And the same is true even for S in the discount market. We're making all 25 tons available. So the total of 100 tons of solvent-based demand between the premium and discount market, we're maxing those out. That's not true for our fuel additive. So we can see that for the premium market, the sales tier 1 market, sales tier 1 market, our fuel additive is being maxed out. We're making all 50 tons of demand in that market. But we're not making any fuel additive for the discount market. So essentially, the way that we would interpret this solution is we are buying additional material 3 to fill out all of our premium and discount markets for solvent base and our premium market for fuel additive. But it's not worth procuring any additional material 3 from supplier B to make any of the fuel additive for the discount market. And we can see here a reduced cost of minus $13.02. So either the price that we're selling or the price of that discount market for fuel additive has to go up by $13.20, or the cost of this material 3 from supplier B has to come down by $13.20 in order for us to economically produce any fuel additive. So that's how you interpret the solution. And that's really the concept around marginal economics, is we've got room for incremental activity to make additional fuel additive and sell it into a discount market, but it's not worth it because our material supplier B is pricing our input material 3 too high. So to test this, just so folks don't think I'm making this up, we can actually come over here to the supplier B material 3. We can drop this price. Let's just drop it to 22. Okay, that's well above that $13.20 threshold. Let's come back and rerun this and see if we make any additional fuel additive to sell into that discount market. And immediately we do. We see right here that we make additional fuel. So we're still maxing out our solvent-based production for the premium and discount markets. We're still doing that, 75 and 25. We're still maxing out the fuel additive for the premium market at 50 tons. And now we're also producing our fuel additive for sale into the discount market or sales tier 2 market, and we're making all 15 tons. So the reason this is important to read through these and understand this is in a business environment, when you run these models with these pricing levels and these demand levels, you're going to have to interpret those results. And understanding that $13.20 break-even value is important, because if that supplier comes to you the next day after you've run your model and says, hey, we're going to cut our prices in half, if that exceeds that threshold, that break-even value, you can know right then and there that you can go ahead and pull the trigger and buy that material. You don't have to rerun the model. Similarly, if that discount market pricing were to come up by $20 the next day due to some other outage from a competing supplier or manufacturer, then hey, you could go ahead and procure more material 3, knowing that that pricing supports it. So that's really the concept behind the marginal economics and what I really wanted to cover today. We can do the same sort of analysis down here with our constraints, but we've covered those in the past, and you can still see down here, material 3 is constraining in this situation. We see our constraints now on product demand. So this shows you what if we were to, I guess, go find some additional customers or additional demand in these premium markets or these discount markets, here's how much that would be worth to us. So that's that dual value, right? That limit cost for these demand levels. But that is essentially the concept of marginal economics and why it's really important to understand it, because I think is folks will find if they apply this to their real world business environment, you often do have more complex situations where you've got multiple markets or customers, and they're not going to be the same across the board. So understanding the trade-offs and the relative costs and availability and pricing amongst them is really important to being agile as an organization. So that's it for this episode. We have one more episode in the series, so that will be hopefully coming up here shortly. And then after this episode 3 series related to production resourcing, we're going to move on to some new topics. So thanks again, and we'll see you soon.